So yeah, it's been a great experience. YRI has been life changing. Ishan has been a really good mentor and friend of mine. I've been talking to him for a while, and the amounts of confidence, the amounts of ambitions he has in me, I think is pretty crazy as well. And he really reads everyone's mind here. So that's a huge thing about YRI and Ishan. So yeah. Yeah, so firstly, of course, publishing of research itself is like a huge privilege here because staying in India, I don't see much, any of my friends, not much. I don't see any of my teachers do that as well, right? So when a high schooler does that and publishes that top journals and conferences, of course, it's like that emotional and that that kind of independent confidence that gives you it just hits you the back of the mind and just says that, oh my god, like I've achieved much things, I've achieved so much. So that mental confidence, that kind of stability, gives you like huge pluses in your entire career and in your entire profile as well. It just doesn't look fancy in college applications, but it gives you that kind of feeling that when you publish a paper, it gives you that kind of thing, okay, wow, I've done something that's pretty crazy and that can really help the community. So we've been working on something called transformer genetic algorithm co-optimization for neoantigen prediction in cancer immunotherapy. So of course the title looks very vague and it looks super vivid as well. So what we've been trying to do is to find like a more like the better neoantigens for cancer immunotherapy, and the dataset that we have used is called TCGA SKCM dataset. We have extracted like a portion of that from the C bio portal is what I've mentioned here. So this is basically like the agenda that we're going through, right? So let me just go through it. So yeah, as I was saying, we have used about 442 melanoma samples from the C bio portal. So the primary reason why we use melanoma samples was that it basically has like a high mutation burden, and it has like multiple mutations which is caused by UV radiation and all that, which it really increases their candidacy for immunotherapy selection. So that's why we basically chose. So as I was saying, let's move on to data types right now. So these are not like general data types. These are mostly medical based data types. So we have something called missense mutations, and then we have beta values, and then we have gene expression, and then we have CNVs, and then we have HLA binding affinities. So since we were running on computational constraints as well, we decided to use like a more peculiar set, which is about 50 samples. And we had extracted about 30,450 neoantigens from those 50 samples, which we got from our transformer model and our genetic algorithm that we have created over the years. And right now, so we have a mean AUC of about 0.9752, which is exceeding most of the SOTA models currently. So I'll be discussing more about that in the next slides, where right now here's and the main reason why we again chose melanoma significance was like basically it had like a high mutation burden, and about the BRAF mutations is about 50%, which technically means that it's like the key drug target. So that's why BRAF is always around the table here. And then you also have clinical impact. So we have two primary metrics here, which is the R value and the P value. So the R value is about 0.316, which means that there is about a moderate positive correlation between the two axes, and that's what it means by R. And then we have P is about 0.028, which is statistically significant, which also means that it's not just random. It's definitely significant, right? And and one of the neoantigen IDs was TCGA-D3A8GK, which had about 757 for high quality neoantigens. So this clearly shows that our pipeline can give you one of the best neoantigens that can be presented for a particular ID. So that's what we actually wanted to depict here. And our model performance is based on three main values: binding affinity, immunogenicity, and stability, which is about 0.9830 and 0.9803 and 0.9624 respectively. Right, so let me just move on to the next one. So next one is the multi-omics data and observations. Right, so as I was telling, there was about 30,450 neoantigens that we had extracted. So why we had extracted multiple neoantigens was just because for the high immunogenicity and missense mutation score, so that we can have like a really good combination of good neoantigens for candidate, and for vaccine selection. And for feature engineering, we had built features from sequence embedding, chi-Doolittle hydrophobicity, and binding affinity scores. So sequence embedding is basically like when you want to convert protein into numbers. In chi-Doolittle hydrophobicity is just to measure the amino acids if they are like water resistant or they're water prevalent or something. And then we have variance, which is about 0.123, which indicates strong diversity among the neoantigens, not just stingent towards one particular diversity. And again, as going forward, for the pre-processing, we had used batch normalization and z-score standardizing for transform model techniques. And okay, now coming to the main point, we have hypotheses and model design. For the for the hypothesis, we created a transform model with evolutionary optimization. We had used something called NSGA2, and also we had developed a genetic algorithm which had given us an AUC score of all that I had discussed below. And also we had a target AUC of 0.7, which we had definitely exceeded. So 0.7 was our baseline model of what we were thinking, but I think it turned out pretty good. And then for model architecture, we have 6 layers and 8 heads, which basically means that you have like 6 blocks on top of each other, and 8 heads is nothing but multi-head attention, where you can view the data in 8 different types. And and the learning rate was about 0.001 and batch was about 32. And yeah, of course, the top neoantigens is just mentioned here. And for the key features already, as mentioned, we use binding affinity, which is about IC50 was about less than 500 nm, which also technically means that the lower the IC50, the better it is. And then on we also about the training, we had with our fine-tuned GA model and with our transform model, we have received about 0.9752 as our mean AUC score, area under curve. And we have performance as well. The precision is about 0.94, recall is about 0.92, and F1 is about 0.93. Right. So basically, the way we ran the model was on Google Colab and local systems as well. So we use the NVIDIA A100 GPU to build more scalable and a more reproducible pipeline so that we can use it everywhere, right? And the robustness, we use the 5-fold CV, which is basically like a computational method where it's not even cross validation, and we had a variance stability of about 0.123 as well. So these both factors ensure generalizability as well as reproducibility. And for the last part, we have experiment results and performance. So this is like the super important part here. So if you can see here, we have the ROC score and for binding affinity, immunogenicity, and stability as well. So what you can see here is there like there's like a hockey stick kind of graph, which is expected, because this shows that it is not just random, but it's on the high end of predicting ROC. So as I told you, the mean AUC was about 0.9752, while our target was about 0.7. So, and we have like individual AUC scores that is mentioned and is also represented in the graph here. And and for the additional metrics, the precision was again over 0.94, and the processing efficiency was again mentioned. So this was primarily showcased here to really understand how the RC growths kind of came together, and they were not just random. This took a lot of time for us to really get a hockey stick kind of graph, because that is what is expected, and most of the graphs are not just hockey stick, they're just like a huge concave curve, and it's really not expected. But when you have a hockey stick, it really ensures that you have a good robust model for reproducibility. And next we have the average model predictions by task. So since we used a 5-fold CV, it kind of confirmed that we had really good robustness while not just using like other instrumental methods as well. So our threshold analysis were like the initial ones were about 0.279, and then the immunogenicity was about 0.443 and peaked up to 0.9830 and 0.903 respectively. And we also had something called top quartile threshold, was about 128.241, which kind of, so that particular quartile kind of gave us like 0.9319, which kind of gave us a good stability retention of over 90%, and that's what we kind of did, right? So now I'm going to be referring to one of the papers that I had used as well. It's called Wang 2023, right? So they had used a random forest model, which gave them a 0.85 AUC, and ours had definitely got above by 0.14, 0.10%, and 0.6%. So we can really well say that our model really worked well by using our own custom transform model rather than using random forest or something. And then we have vaccine candidate selection, where our genetic algorithm optimization scored the best candidate at 0.9395. So this kind of showed us that at this particular score, there was about 64957 and 7574 neoantigens per sample. This clearly shows that from GA optimization scores from plus 0.9, we had like high quality neoantigens across per sample, which was really good because it really shows that uh, higher neoantigens give you high survival rates, which was also showed by. So our key findings that we had achieved SODA mean AUC and task-specific AUCs, and we had outperformed Rank 2023 by 0.6%. This could also be due that we created like a custom data set for training and testing as well, which kind of might have given the hump, but overall, this kind of created a really good model for reproducibility as well as high AUC scores. And the clinical scores gave us good survival correlations about which kind of supports neoantigen burden as a biomarker for immunotherapy, right? So, and then for limitations, we had a small sample size. We had about 50 SKCM samples and top quartile variability. So the AC sometimes be 0.5, which might limit generalizability, right? So that was something that was something that I told you about, because when you decrease the sample size, the amount of technicality that goes into it might decrease as well. But taking into consideration, other such SODM models, I think we did a pretty good job on that as well. So the future work is that if we could scale this TCGA melanoma dataset to multiple datasets from TCGA or BioPortal, CBioPortal as well, I think it would be pretty crazy, because if you're going to be able to integrate multiple protein embeddings into like a single model, it's going to be super efficient and it can be really clinical based as well. And our innovative applications were going to be if we could get like a genetic algorithm optimized neoantigen vaccine, which could do real-time clinical translation, right? And the model refinement could also be like using a multi-model learning, using imaging, and then using photomegs and to improve stability predictions as well. And the scalability goals, we are enabling 100K plus neoantigen real-time processing with cloud-based GAs and multiple GPU clusters, which do happen for high clinical base. And collaborative research, yeah, of course, this is a lot, but yeah, I'm expecting that. Yeah, and yeah, thank you very much. First time I looked at YRI was through a friend of mine who got into YRI, but I don't think she joined. So I was like super intrigued, because when I saw like when you can publish IEEE papers and JAMA papers with high schoolers and with PhDs, I think that's super fancy to really put out, but I really didn't think it was like legit at first. And then I just applied, and the next day I just got my acceptance, and it was like pretty cool, to be honest. And then I hopped on a call with Ishan, and he gave me like super entire confidence on how this worked, the entire framework, and the entire process of how it's going to be working. I think that's something I really appreciate, because I really don't see this happening at multiple organizations, which are like super huge, and they just don't give out the right resources to students. And I've done really good job, and it's like super fun here. I've had a great time working with my PhD over the weeks, and I of course I can see real good feedback from him. It's not just like I just go give my paper to him and he just says yes or no. He just gives me real feedback, which I really appreciate. So yeah, it's been a great experience. YRI has been life-changing. Ishan has been a really good mentor and friend of mine. I've been talking to him for a while, and the amount of confidence, the amount of ambitions he has in me, I think is pretty crazy as well. And he really reads everyone's mind here. So that's a huge thing about YRI and Ishan. So yeah. Yeah, so firstly, of course, publishing research itself is like a huge privilege here, because staying in India, I don't see any of my friends, not much. I don't see any of my teachers do that as well, right? So when a high schooler does that and publishes at top journals and conferences, of course, it's like that emotional and that, that kind of independent confidence that gives you, it just hits you the back of the mind and just says that, oh my God, like I've achieved much things, I've achieved so much. So that mental confidence, that kind of stability, gives you like huge pluses in your entire career and in your entire profile as well. It just doesn't look fancy in college applications, but it gives you that kind of feeling that when you publish a paper, it gives you that kind of thing, okay, wow, I've done something that's pretty crazy and that can really help the community. So yeah,